Hey all you cool cats and kittens, it's time for another video lecture. So yesterday's video lecture, we started talking about stoichiometry, and we did a few stoich problems. Remember that stoichiometry problems look a little bit like this. We've got our reaction, and then we've got our story problem. If 5 moles of methane, that's the CH4, if 5 moles of methane are combusted with excess oxygen gas, how many grams of water are produced? I would use my mole bridge here. This reaction is already balanced for me. So the ratio, the mole bridge, is 1 to 2. If 1 mole of methane goes in, 2 moles of water come out. So if 5 moles of methane go in, 10 moles of water come out. The ratio stays the same. That mole bridge will stay the same, even if the number is actually changing. So 5 moles go in, 10 moles of water come out. How much is that in grams? Well, the molar mass of water is 18 grams per mole. So I could do this with algebra, or I could do it with dimensional analysis. But I would figure out that it's 180 grams of water. 18 times 10. If you still feel like you need help on problems like this, you can rewatch the video from yesterday. You can take a look at that guided practice that I posted. Ask in the chat room. Come to office hours. Lots of ways to get this down. So we're going to continue to talk about stoichiometry today, but we're going to kind of introduce another little wrinkle into these problems, another little twist to these stoichiometry problems. And to do that, we're going to start off with a thought experiment. It's peanut butter jelly time. Here we go. So, our thought experiment here, all in our heads. Imagine that you're throwing a house party. You got all your friends over, and you're going to serve them peanut butter and jelly sandwiches. That's what they want. That's what you got. They're getting peanut butter and jelly sandwiches. But you only have these ingredients. You've got 20 slices of bread. You've got 3 portions or 3 servings of peanut butter. And you've got 10 portions of jelly. How many peanut butter and jellies can you make? You can't make just jelly sandwiches. You can't skimp on the peanut butter. They've got to be full sandwiches. So you can actually only make 3 peanut butter jelly sandwiches. It doesn't matter that you've got all this leftover bread and all this leftover jelly. You're still only going to be limited to those 3 sandwiches because then you'll run out of peanut butter. You can't make any more. This is going to relate to chemistry, I promise. So, this whole idea with the peanut butter and jelly sandwich. One thing will run out before the other things. In this case, the peanut butter ran out before the jelly did. Another kind of classic example is like chips and salsa. You go to the store, you buy a bag of chips and a bottle of salsa or whatever. You're eating the chips and the salsa, and then you run out of chips. So you have to go to the store and get more chips. But then you run out of salsa, so you have to go to the store and get more salsa. But then you run out of chips again, so you have to go back to get more chips. They're not going to run out at the same rate. One of them will probably run out faster than the other one. We call that the limiting reactant. Limiting reactant. You're going to want to get a definition down for the limiting reactant here. Chemical reactions are really similar to that peanut butter and jelly analogy or the chips and the salsa analogy. It doesn't matter if you've got plenty of some of the reactants. If you don't have enough of just one of those reactants, that's like the peanut butter, you're gonna run out and the reaction will stop. So this last sentence, I would go ahead and get this down in your notes. The reactant that determines the yield of a chemical reaction is known as the limiting reactant. One of your chemicals is going to run out first. Whichever one runs out first, that's the limiting reactant, and it determines our yield, the product. It tells us how much product we'll make. On our analogy here, our yield was 3 peanut butter and jelly sandwiches. And that yield was determined by the peanut butter. I only had 3 portions of peanut butter. I could only make 3 sandwiches. The peanut butter was the limiting reactant. So that's great. Hopefully we've got the idea that one of these things is going to run out before the other thing does. It's limiting. Now let's apply that to an actual chemical reaction. We're going to move away from food analogies. We're going to look at the actual chemistry. What does it look like in a real reaction? So let's consider this chemical reaction. This is a way that we can chemically produce water by combining hydrogen gas and oxygen gas. And this reaction is already balanced for me. 2 moles of hydrogen gas, 1 mole of oxygen gas. I'm going to produce 2 moles of water. But now let's look at the story problem bit. If 1 mole of hydrogen gas and 1 mole of oxygen gas react, how many moles of water are made? Well, I've got 1 mole of each. So it seems like I've got the same amount of both things to start with. The problem is they're not going to run out at the same rate. This reaction is using up twice as much hydrogen as it is oxygen. That's because there's twice as much hydrogen in water as there is oxygen. The percent composition I should just say the composition is a little bit off there. So if we see how this would play out, if I've got 1 mole of each to start, I'm going to run out of one of them first. I only have 1 mole of hydrogen gas. So I can't even meet this 2 moles that I'm supposed to be starting with. I can only use the 1 mole. And then I'm only going to use half a mole of oxygen gas to produce 1 mole of water. Don't get too upset with this half a mole over here. Remember that a mole is just a counter, and it's a very big number that it's counting. So half a mole is still 3.011 times 10 to the 23rd molecules of oxygen gas. It's still a lot of oxygen. What I'm getting at here, one of these chemicals ran out before the other one did. I had 1 mole of each to start. I ran through 1 mole of hydrogen gas, and in that same amount of time, I only ran through half a mole of oxygen gas. The hydrogen gas is the limiting reactant here. The hydrogen gas is the one that ran out first. It's the one that determined the yield. I only had 1 mole of hydrogen gas. I could only make 1 mole of water. So that's kind of how these problems are going to look. Let's keep going here. How do we know which reactant is limiting? How do I know which one is going to run out first? Sometimes it'll be real easy for you. If you see one of these bolded words, that's a big hint for you. If one of the chemicals is in excess or in abundance, that means you've got a bunch of it. You've got more than you need, an excess of it, an abundance of it. It's not going to be limiting. The one that's in excess, the one that's in abundance, is not limiting. It tells you that the other one is limiting. The other one will run out first. Now, unfortunately, life is not always so clean. I'm not always going to be able to tell you that it's in excess or it's in abundance. So if I don't tell you that, if I don't use those words, you're actually going to need to solve the problem twice. If the problem doesn't give any easy hint, you'll have to calculate the yield for both reactants, or all reactants if there's more than 2, and then go with the smaller yield. Remember that these are limiting reactants. You are limited to the smaller number. You're limited to whatever the smaller yield is. Let's look at one example before we go inside and do some on the whiteboard wall. So one example here. Let's see if I can move my face out of the way. So we're looking at this same simple reaction. Hydrogen gas, oxygen gas, water. If I've got 20 grams of hydrogen gas reacting with 20 grams of oxygen gas, how many moles of water are produced? It doesn't say excess. It doesn't say abundance. I'm gonna have to solve this problem twice. The first time I'll solve it for the hydrogen gas. I'll start with grams of hydrogen, I'll go to moles of hydrogen, I'll go over the mole bridge. And I would find out that 10 moles of water were made. 10 moles of water. That's for hydrogen. That's one answer. Now I've got to do it again. I'll do it again for oxygen. When I do this same problem for the oxygen gas, I start with grams of oxygen, and then moles of oxygen, and then I go over the mole bridge. This time I'm only going to get 1.25 moles of water that are produced. So I'm getting conflicting answers here. The hydrogen tells me I'll make 10 moles. The oxygen tells me I'll only make 1.25 moles. I am limited to the smaller amount. I'm stuck with that smaller yield. So oxygen is my limiting reactant. I'm only going to make 1.25 moles of water. I'm only going to produce that much water. That's because the oxygen will run out. I'll run out of oxygen, and then the reaction won't be able to keep going because I'm missing one of those reactants. All right. So it's one thing to sit here and just kind of talk through these problems. It's going to be much more helpful if we can actually see the work, see the stoichiometry to get to these answers. So we are going to try 2. I'm going to head inside here. I'll do 2 problems for you on my whiteboard wall, and then you have 3 more problems for homework tonight. So let's head in. Let's get it doing. Let's get it doing. Let's get it doing. Okay, so for our first example, let's stick with the same reaction that we've been looking at a lot in this video. We're making water still. 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water. And then my story problem says, if 40 grams of hydrogen gas react with excess oxygen, then how many grams of water are produced? I'm going to go ahead and follow my question word here. How many grams of water? That's what I want my answer to be in. Grams of water. So I'm trying to get there. I see another really important word here too. Excess. Remember that that's one of our big hints. If we see excess or abundance, it's going to immediately tell us which reactant is the limiting reactant. Now this problem says that I have excess oxygen. So I've got plenty of oxygen. I'm not going to run out of oxygen, but I've got a limited amount of hydrogen. This is a pretty common thing to happen with this particular reaction. There's plenty of oxygen molecules just in the air, but then there's kind of like a limited amount of hydrogen with which to do this reaction. So I've got excess oxygen. That means that the hydrogen is the limiting reactant. Because I know which reactant is limiting, I only need to solve this problem once. In the next example, we'll look at one where we have to solve it twice. But let's go ahead and do this stoichiometry for this problem. I know that I'm working off of the hydrogen, and I have 40 grams of hydrogen. I like to start there. So my first fraction, 40 grams of hydrogen. I'm starting with what I'm given. I know that these grams of hydrogen will need to cancel out. I know that I need to get to moles of hydrogen so that I can do the mole bridge. When you've got moles and grams in the same fraction, you're looking at a molar mass. In order to find that molar mass, we use the periodic table. 1 mole of hydrogen gas It's 2 atoms of hydrogen, about 2.02 grams in that ballpark. So I went from grams to moles. Now that I'm in moles, I can go over that mole bridge. 2 moles of hydrogen will produce 2 moles of water. So you may notice that the actual values here, 2 over 2, it's not changing the value of these numbers at all, but it is changing the unit, which is what I wanted to happen. I want to go over the bridge from the reactant side to the product side. I've just got one more step here. I want to get how many grams of water instead of moles of water. So for this last step, let's change those moles of water into grams of water. So again, I've got grams and moles in the same fraction. That tells me that I'm going to do a molar mass. I'm going to need to use my periodic table, look up hydrogen, look up oxygen, and calculate that molar mass. I know that the molar mass of water is about 18 grams per mole, just because I've worked with water a lot. My stoichiometry is set up now. I could show that my units cancel. Grams hydrogen, moles water. The only unit I have left is grams of water. How many grams of water? I'm in good shape. From here, I would go ahead and multiply and divide to solve. This is going to be just about 360 grams of water. So, from the top here real quick, I saw that I had excess oxygen. That tells me right away that oxygen is not limiting. Hydrogen must be the limiting reactant. If I know that hydrogen is the limiting reactant, I only need to solve this problem once. I'll solve for hydrogen, which I did in these 4 steps, and I figured out my final answer. Theoretically, I would make 360 grams of water if I did this reaction with 40 grams of hydrogen and just like an abundance of oxygen. That's the nice way when I tell you that there's an excess or when I tell you that there's an abundance. You are crossing your fingers and hoping that I tell you that. But I won't always do that. Sometimes you're gonna have to go ahead and solve the problem twice. Let's take a look at that in our second example here. Alright, so we're going for uno mas with our examples. One more example here, and then we'll wrap it up. I switched up the reaction this time. This is also a reaction that we're familiar with. This is one that we've all done. Zinc and sulfur combining to make zinc sulfide. It's a synthesis reaction. Zinc and sulfur, zinc sulfide. It's already balanced. This is a pretty simple reaction here. My story problem. If I have 5 grams of zinc and 5 grams of sulfur, and they're reacting together, how many grams of zinc sulfide are produced? How many grams of zinc sulfide? That's what I want to find out. Now, at first glance, it might seem like I've got the same amount of both. And in a sense, I do. They both weigh 5, or they both have a mass of 5 grams. 5 grams of zinc, 5 grams of sulfur. But remember, each molecule or each atom of zinc and sulfur have different masses. So just because they have the same mass does not mean that there's the same number of molecules or moles in those reactants. We're going to actually have to do the stoichiometry to figure it out. Now, I don't have any clues this time. It does not say excess. It does not say abundance. It's giving me actual amounts for both of these, 5 grams for each. This is a case where you will need to solve the problem twice. You're going to need to solve it from the zinc perspective and from the sulfur perspective and just see which answer is smallest. Remember that we're limited to the smaller answer. So let's go ahead and work through this example here. I'm going to start with zinc. So starting with 5 grams of zinc, I can carry that unit down, grams of zinc. I need to get into moles of zinc so that I can go over that mole bridge. So let's convert this into moles of zinc. I would look this up from the periodic table. The atomic mass, or the molar mass of zinc, I got it written down here, about 65.38. I found this from the periodic table. So 1 mole of zinc is about 65.38 grams of zinc. My mole bridge is really easy this time. It's 1 to 1. So this is not actually going to affect the value again, 1 over 1. It's not changing the value at all. It's just letting me switch units from moles of zinc to moles of zinc sulfide. And then my final step, I'm going to convert those moles of zinc sulfide into grams of zinc sulfide. How many grams of zinc sulfide? This is another one that I would need to use my periodic table for. I would look up zinc, I'd look up sulfur, and I would add those values together. I did this in advance. It's about 95.9. So there's my setup for the zinc problem. I started with grams, I did a molar mass. I did the mole bridge, I did another molar mass. And then my final answer here, I'm going to produce, with significant figures, about 7.3 grams of zinc sulfide. That might be my final answer. That might be the answer that I end up going with. But I don't know for sure yet. I need to do it for sulfur next. I need to do the same work, just from sulfur's perspective, and see if I get a larger or smaller answer. I'm still starting with 5 grams. This time it's of sulfur. My next step is going to look pretty much the same. I'm going 1 mole of sulfur. How many grams is that? The only difference is the value here. The number is changing because I'm doing it for sulfur instead of zinc. I would look this up on the periodic table. Sulfur is one that I know. It's about 32.06 grams per mole. I go into the mole bridge. Again, it's 1 to 1. 1 mole of sulfur produces 1 mole of zinc sulfide. And then my final step is identical. It's the molar mass of zinc sulfide. It's the same numbers here and units. That's because once I've crossed that mole bridge, once I'm over the mole bridge and I'm in the product side, these two problems are going to look the same. They're both dealing with zinc sulfide as the product. So this middle step, the mole bridge here, once I've gone over that mole bridge, this final step is identical for both problems. The only thing that's really different for these problems is this first molar mass. Am I basing it off of zinc or am I basing it off of sulfur? Let's go ahead and solve here, see what we get for the sulfur perspective. If I multiplied and divided there, using my significant figures, I would get about 15 grams of zinc sulfide. So I've got 2 conflicting answers here. The zinc is going to tell me I'll make 7.3. The sulfur is going to tell me I'm going to make about twice that much, about 15 grams. I am limited to the smaller answer. My answer this time is the 7.3 grams of zinc sulfide. You probably can't see that. 7.3 grams of zinc sulfide. What's going to happen is that I'm going to run out of the zinc before I run out of the sulfur. Zinc is heavier than sulfur is. It's got a bigger atomic mass and molar mass. So even though I've got 5 grams of zinc, that zinc is going to run out faster than the sulfur will. It's limited by the zinc in the reaction. So this is the most work that you would have to do for a stoichiometry problem like this. If it doesn't say excess, if it doesn't say abundance, you're going to have to solve that problem twice, and then go with the smaller answer. Your homework tonight is 3 problems. One of them is like this, where you'll have to solve it twice. I think I was pretty nice on the other ones, and I told you either excess or abundance. Definitely come to office hours if you need help. I get lonely just sitting there reading my book by myself, so come say hi, even if you feel comfortable with the chemistry. Alright, that's it for today. I will see you again tomorrow.